Welcome to the Walton Pi. Today we are going to be talking about the Fundamental Theorem of Calculus. Now, this theorem is very, very important to understand because it bridges the gap between derivatives and integration. It makes the connection very solid, and it's one of the most important theorems to understand. In fact, it's the most important theorem in calculus, which is why it gets the name of the Fundamental Theorem of Calculus. There's a bunch of other theorems, but this is the main one that is very important to understand. So the general idea of the Fundamental Theorem of Calculus, it's broken up into two pieces. And so the first part tells the connection between what it means to take a derivative and to take an integral. And then the second part connects definite integrals with the general antiderivative of a function. So let's look at part one. Part one of the Fundamental Theorem of Calculus says, if f of x is a continuous function from a to b, then the function big F of x, where big F is equal to the integral from a to x of f of t dt, that is continuous on the interval a to b, and it's differentiable on the open interval a to b, and the derivative of big F is little f. This is a really, really important thing to understand. What it says is the derivative of an integral, as long as the integral has x's in it and is not a constant value, so it's not a specific answer, or not a specific like real number result, if there's x's in it, the derivative of an integral is the original function. So in a sense, derivatives and integration, those are inverses of each other. So let's do an example. So if big F is equal to the integral from 7 to x of 13 sine of 4t e to the 7t squared dt, if we want to figure out what is f prime of x, meaning the derivative of big F, we don't want to have to integrate that and then take the derivative. First off, I don't know how we would even bother integrating that. That is a very complicated thing to try and integrate. But taking the derivative of this integral is actually very straightforward. We can just use the Fundamental Theorem of Calculus. So if we take the derivative of big F, that's just f prime of x, we can plug in x everywhere there was a t. That is what the Fundamental Theorem of Calculus says. So the derivative is 13 sine of 4x e to the 7x squared. Let's do another example of this. Let's say that we are integrating from x to 9 of 7t cubed minus 16 tangent of t plus 3 pi over 4. What's the derivative of that? If we want to just plug in all of the x's where there's t's, that's not going to give us the right answer, because this is not in the form that the theorem says. The theorem is true if it goes from a constant to x, not from x to a constant. So we have to first rewrite f in terms of the integral from a constant to x. So we can switch our bounds if we add a negative out front. So that means that big F of x is equal to negative the integral from 9 to x of 7t cubed minus 16 tangent of t plus 3 pi over 4. Now it's in the correct form. So now we can replace the t's with x's when we take the derivative. And so when we do that, we get negative 7x cubed plus 16 tangent of x plus 3 pi over 4. That's an important thing we have to remember. If it doesn't match the form in the theorem, it's not quite ready to just replace the t's with x's. For a third example, let's say that f of x is the integral from 7 to sine of x of t cubed e to the t minus 6 dt. What's the derivative of this? Well, it's close to the right form. It's a constant to something in x, but the problem is it's not just x. So this is where we're actually going to have to use the chain rule. So we are going to have sine of x cubed times e to the sine x minus 6, but then we have to multiply it by the derivative of sine of x. So we are going to multiply it by a cosine of x. So we have to remember the chain rule if it's not constant to x. If it's a constant to a function of x, we are going to need to use the chain rule. So if we combine part 1 with the chain rule, this is what the Fundamental Theorem of Calculus essentially says. If big F is the integral from a of x to b of x, where a and b are both functions of x, of the integral of f of t dt, then the derivative of big F is going to be f of b of x times the derivative of b minus f of a of x times the derivative of a. So you can either remember this or you can remember the general form, and remember that if it's not constant to x, you have to use the chain rule. So let's now talk about part 2. So part 2 of the fundamental theorem of calculus says that if f of x is continuous on the closed interval from a to b, then the integral from a to b of f of x dx, so a definite integral, that is equal to big F of b minus big F of a, where big F is any antiderivative of little f. Now this is really, really powerful, because for a given function, there are infinitely many antiderivatives. But this says it doesn't matter which one we pick. We can pick any function that's an antiderivative, and we can plug in b, we can plug in a, and take the difference between the two. This is a really, really powerful theorem. So, for an example, let's try and figure out what's the integral from 3 to 8 of x squared. So, if we can find an antiderivative, this is just going to be the antiderivative at 8 minus the antiderivative at 3. The challenge is, what antiderivative should we pick? Well, one antiderivative is x cubed over 3 plus 17.2. That is a valid antiderivative. It's not the only one, there's infinitely many others, but this is one that we can pick. So we can evaluate that at 8, and we can evaluate it at 3. So we get 8 cubed over 3 plus 17.2 minus 3 cubed over 3 plus 17.2. So that gives us 512 over 3 plus 17.2 minus 9 minus 17.2. Our 17.2's canceled, which means we're really just getting 512 over 3 minus 9, which is 485 over 3. So that's our answer. But the big question is, since the 17.2 is canceled, did it matter which one we picked? No, we could have replaced 17.2 with any constant. And so that comes up with a useful tip. If we have the integral from a to b of f of x dx, since we can choose any antiderivative, we might as well choose the antiderivative where the plus c at the end is 0. So in our previous example, we could just as easily have picked big F to be x cubed over 3 plus 0, and then we wouldn't have had those 17.2's that would have had to cancel. They would have already been gone. So let's use that tip to find the integral from 0 to 4 of e to the x dx. Well, we can take the antiderivative at 4, subtract the antiderivative at 0. Since the antiderivative is e to the x plus c, let's just use e to the x plus 0, so that becomes e to the 4 minus e to the 0, which is just e to the 4 minus 1, and that's our answer. I hope this video was helpful. Please check out some of my other videos, and please like and subscribe if you haven't already, so that I can continue to make these videos. I hope you all have a great rest of your day, and good luck with the rest of your math.